I'm still imaging faults. Before I was doing primarily kind of a mapping and filtering operation. And I switched over, and just this month I've been doing migrating. So I'm going to show that. So this is the outline for my talk. I'm just going to start out with a little bit of motivation behind why we're doing this. Just outline some basic theory. And then I'll talk about two things. One is the 2D fault, what we're calling 2D fault imaging, and that would be inline on a 2D line. Give an example of synthetics, show the processing flow, and talk about a field result that we collect up here in Houston. And then I'll talk about 3D fault imaging. This is imaging faults that are offline. And I just have synthetics for that, and I'll finish with a summary. So the motivation is, well, there's a couple of things. You can want to identify vertical features. And you can see the picture right there. I'm sure the gentleman probably would have wanted to identify that before building his house. E-Ray later is going to talk about identifying faults in Haiti. So that's one aspect of it. But another aspect is just to better image lateral heterogeneity. And I actually just saw a nice talk by Peter Pullitz. I've got a couple of images there I just pulled from his abstract. And he was talking about, he was looking at data from Saudi Aramco, and he wasn't able to parameterize his anisotropy down deep very well because he didn't have a good static solution in the near surface. So in his abstract, there's a little example there where he used the standard statics, and he got a much better stack with correct statics, accounting for lateral heterogeneity more. Another thing is that he had in his lecture was pretty good examples of backscattered ground roll. And I just pulled another one from his abstract. So the overall motivation is to possibly characterize this in the near surface better, and I might be able to better design reject filters. So that'll go on to the theory. When we talk about ground roll, usually we're talking about the Rayleigh wave that shows up on our vertical component. It's the coupling of the P and the SV wave at the surface. And you can see the direction of propagation of our ground roll, and the particle motion is retrograde, and it diminishes as it goes down. And that's shown on the plot on the right there, where you have, I plotted out Rayleigh wave vertical displacement for a shear wave velocity that's at 300 meters per second. And this is just relative displacement. So you can see it decays as it goes down in depth. The interesting thing about it is that if you look at different frequencies, so if you have a wave field that has different frequencies, here I plotted 40 hertz to 4 hertz, your higher frequencies are only going to be seeing that shallow layer, and these are going to be kind of detecting down deep. So if you have something like a layer cake model here, that's how the people that do shear wave inversions invert for shear wave velocity as a function of depth by looking at what the wave field is doing as a function of frequency. So we're going to use that as well. So I'm looking at back reflected ground roll just to go over my notation here. Looking at O, outgoing. So I define everything as outgoing from the source, gets some sharp discontinuity, and then it comes back as incoming surface waves. And there's this interesting relationship between depth and frequency that the ground roll is going to have. So what does it look like in data? We've got a couple of pictures here. On the left is from a physical model that we did here. Up there in the upper right, you can see we have plexiglass and aluminum. And we recorded just a 2D line. And this is what it looks like down here. So you've got your P wave. This is your ground roll. That's your outgoing ground roll. It refracts, and then you've got your backscattering. There's some other interesting things. You do get conversions. There's a reflected P wave conversion, or I guess that's just reflective P wave, but there will be convergence. You can't really see it on this one, but there are conversions to P sometimes on the backscatter. On the right is an example from the Hockley Fault that's just north of here by the premium outlet malls. There you can see the back reflection quite nicely there. So our objective will be to get at this point right here and get the reflectivity. So to kind of show the processing flow that I'm using, I'm going to use a 2D model. This is a 2D model I'm using. It's kind of a blind fault model. I've got a consistent near surface velocity and two different velocities down below to cause reflectivity right here. There's my parameters down below. And again, what I used for this synthetic example is a spectral element modeling program at SpecFDM. So here's your ground roll, the outgoing. There's the incoming. And this is an extracted dispersion curve similar to what you saw before, the phase velocity versus frequency diagram in the talk before. This is dispersive as well. So what I'm going to do is apply a filtering to get at reflectivity that occurs right here. And you can see the major problem here is that the outgoing wave covers up my incoming wave. So I want to take care of that. The type of processing flow I'm going to follow is very similar to a VSP processing flow, so you'll probably recognize it if you're familiar with it. So again, we have these phase velocities extracted here. If we know what the phase velocity is, we can phase match this outgoing surface wave and return it back to the zero, compress it, and return it back to the zero time. And that's what this is showing right here. So I've compressed that outgoing surface wave. Now to get at the incoming surface wave, you can apply a median enhanced out to the outgoing filter, subtract it. Now we've kind of uncovered what's going on here right at that area that we're interested in. And to enhance it, it took a while to kind of figure out a way to enhance this. Right now we're using a back propagation where we back propagate. And then apply a mute around the zero time and deconvolve this. So what we're doing is we're muting and deconvolving the incoming, the incoming by the outgoing. And we get something that we're calling spectral reflectivity. I'm sorry, I guess I wasn't clear on this. This is to get from here to here, all I'm doing is a FFT. So I'm doing an FFT along each trace, just looking at the spectral map of that. And what I'm interested in is the fact that the frequency content of this may be different depending on what depth this blind fault is. There's one last trick that I'm doing. It's a depth mapping. It's what they did with the shear wave velocities initially. Because they knew that at about a half wavelength, they're very sensitive to that depth, that you can do a conversion if you know your wavelength to depth, just using the rule of thumb that it's half wavelength. So that's what I've done here. And you can see the reflectivity is mapped to a depth that agrees fairly well with what my model has. So this is the 2D operation. This is the inline operation. And we attempted this on a field example. This was Hockley that I showed initially. So this is North Houston. There's our line right beside the highway. The fault kind of runs this way. There's the larger map, and then we're blowing up this little area right here. So that little red line is the Hockley fault. So this is the regular process reflection image, and our plan was to use the spectral reflectivity as kind of an attribute now for this. So I'm going to overlay my result on top of this this image. So you can see we've kind of very lightly put in some suggestive faulting And actually, if you were out there, we noted that there is some surface expression of the Hockley fault at that point. So this is the overlay. I guess it shows up pretty well. You can see that indeed I did pick up the same thing in the ground roll data as you do in the reflection data. And also it's interesting that I sort of pick up something over here which agrees with what you might be able to interpret as some kind of channeling up here. So it looks like it's processing something. Okay, so now I'm going to shift gears here. I've been talking about processing everything in line, in the 2D line. Now I'm going to process in a 3D sense. And so what I'm showing here is what I've been assuming, and this is my 2D line. So this is a map view, and what I'm showing is a depth slice at 8 meters. This is a cross section of the same volume, so it's a 3D volume. The green are my receivers, the red is the source, and that's my shot record, resulting shot record here. So everything that I'm assuming when I'm in 2D, I'm just assuming that I'm normal to my fault. So my committee asked me, well, what happens when the fault is offline? So I just cut it off and try to find out what's happening. So I should also mention here, if this looks a bit funny to you, it's because I'm only modeling, this is only ground roll that I've modeled here. And I've used, I guess, a semi-analytic 2D phase shift to model the ground roll, assuming that I knew the phase velocity as a function of frequency. So when you watch this, what you'll be seeing is a snapshot of the wave field on the left and shot record on the right. And again, this is just ground roll. It's nothing else. So there's your outgoing ground roll. You can see it's reflecting off the edge. There it's showing up here. And one thing to note is before this was a reflection coming back. Now it's no longer a reflection. It's really a diffraction off of this corner. And what's coming up here, now that is a reflection. So now my problem is different in that, it's good that my outgoing wave is not covering up my incoming wave, but I need to find a way to get that, get the outgoing and the incoming wave in the same spot so I can deconvolve. Basically do this by migrating the incoming wave and convolving it with the modeled outgoing wave. So the algorithm that I'm using right now, it's a pretty simple algorithm. It's a one-way split-step phase shift. Staffa came up with it with Delphi, and I think some other people were working on this too. And the only thing that I changed was I made this a 2D propagation. So, well, it is 2D, but it's not an X and Z, but an X and Y. I modified it for dispersion, so it could handle dispersion. And my imaging condition is not correlation, but a deconvolution. So those are my modifications. So again, there's my incoming field. This is showing my migration. I'm going to inject. This is what I've recorded, and I'm injecting it back into ground for my migration. This is my outgoing field that I modeled. I'm going to reverse it, and I'm going to deconvolve my incoming by my outgoing to get my deconvolution. I'll just show this. There you can see my resultant deconvolution here. It's showing up in the right spot. And it's actually pretty interesting that these are dispersive waves, but deconvolve them, you get a nice reflection. And so just one last example here before my summary. This is just an example of a more complicated back reflection. So I'm just going to migrate this and show you the result because it looks like there might be some potential to migrating ground roll in this way. So here's again the same operation. I'll just go through this. You can see the image showing up on the deconvolution. So that complicated wave field in the ground roll can image something like this offline. So again, what we're hoping to do, I didn't do it here, but we're hoping to take this, and now because we've pulled along depth information with the frequency content of the Rayleigh wave, we can kind of make this 3D. So as far as the summary goes, trying to say yes, near surface is important to define. It's going to help a lot with statics, defining filters. There is useful information in the back reflected ground rule, especially if you're trying to define sharp lateral heterogeneity. That frequency content has a tendency of, well, we're claiming that it adds a depth dimension. 1D operation becomes 2D, 2D, 3D. And again, deconvolution looks to be effective in imaging, but imaging rapidly. So with that, I should acknowledge really quickly Exxon, who funds me, Chris Crone, and Warren Ross, Tom Dickens, for all the useful discussions, and my advisor, Dr. Stewart.